Okay, welcome to the final part of this one. Looking at this first problem, well, it wants us to take this graph, which is y equals f of t. Know that the graph is defined for all x. There, it says, okay, a of x, oh, I'm not writing, is the integral from 0 to x of f of t. So part A, we need to evaluate what a of 1 is. So a of 1, same thing as integral from 0 to 1 of f of t. So the question is, what is the area from 0 to 1 here? Well, that's like a rectangle. What was my height? I'll say this is a height 3, a width of 1. 3 times 1 is 3. But it's below the axis, so we'll call this negative 3. Okay, well, what does a of minus 3 means? Well, area from 0 to minus 3 of f of t. So if I'm going to draw this on our thing, it's going to be from 0 to negative 3. So we're trying to find this area. Note, because we're starting from the right and going left, this thing is the negative area from minus 3 to 0 of f of t. And so I'll treat it like this first area. And then, we'll have to make sure we put on that negative. So how I'm going to compute this area is, well, I'm just going to break this up into two different shapes. It's a rectangle from negative 1 to 0. It's a triangle from minus 3 to negative 1. So the triangle has a width of 2. It has a height of 3. Area of a triangle is 1/2 base times height. So 1/2 times 2 times 3 is 1/2 of 2 is just 1. So that's area of that part is going to be 3. Area of this rectangle, well, it's 3 tall, 1 wide. So 1 times 3 is also 3. So it means our total area is going to be 6, but remember, it's all below our axis. So it's going to be negative 6, which is going to be positive 6. So this area gives us a positive 6. Okay. So for which values of x does a of x have a local maximum? Well, let's think about this. So I'm starting from here, right? Well, if I go this way, I'm of a bunch of negative area. It's all negative down here. And then I'm going to start gaining area. So right there, that's going to be a local min, because that's the spot I'm going to be really negative, right? Negative, 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 and then I start increasing. So, that looks something like that, right? My area is going down, and then it starts going back up. But we're looking for a local max. Well, if I go this way, remember, if you're going the other direction, the area is flipped. So this is all positive. So my area is increasing, it's increasing, it's increasing. I get to minus 3, it starts decreasing. So that means as I'm going to the left, I'm increasing my area, and then I'm decreasing. That's a local max. So it's going to be at x equals minus 3. Next, I want us to find f prime of 1 and f double prime of 4. Well, let's think about this. If we're given that a of x is the integral from 0 to x of f of t, well, then a prime of x, well, that's just seeing the derivative, right? And from our fundamental theorem calculus, we just know that's just going to be f of x. So what is f of 1? That is. So a prime of 1, it's just going to be f of 1. What is f of 1? It's minus 3. Okay. And what does that mean about a double prime? Well, it means that a double prime, if a prime is just f of x, a double prime of x is going to be f prime of x. So I'm going to erase some stuff because my picture is pretty convoluted. Going back to, cleaning up a graph. We're asked, okay, if this graph was f of x, right? What's the derivative right here? Well, I'm going, let's think. From here to there, I'm going up 3, going over 2. So What is my slope going to be? Well, it's going to be up 3 over 2, so it's going to be 3/2 or 1.5. Okay, so this next one, this is going to be our optimization. So what is the area of the largest rectangle in the first quadrant with one vertex on the origin and the opposite vertex on the graph of the function f of x equals 12 minus x squared as shown in the graph above? Well, first off, we're trying to maximize the area. So our area equation is base times height, right? So if I'm going to call this part B, well, what is our height going to be? Well, we know this height is going to be wherever it meets this curve. And the curve of this is 12 minus x squared. So if my width is B, I guess it could have done width times height. I just said base. I guess that's more so we use that for triangles. But my height of this is going to be just if I plug B into this equation. So 12 minus B squared. So that means the area of this rectangle is just the base of the rectangle times 12 minus that base squared, which I can rewrite as 12b minus b cubed. And the thing with optimization is once you can write whatever you're trying to maximize or minimize in terms of just one variable, in case b, where b is the base of this, to find our critical points where it's going to be maximized or minimized, we're going to take a derivative and set equal to 0. So a prime is going to be 12 minus 3b squared, and we'll say that equals 0. So I'll add 3b squared over, divide by 3, take a square root, so b is going to be plus or minus the square root of 4, which is plus or minus 2. But remember how it said this whole thing with the first quadrant? Negative 2 is over here. That doesn't make sense. So that means positive 2 is going to be it. So we need to find what the area is. So we now know that it's going to kind of happen at like the critical point. Just to double check that this is the correct one, we could technically take a second derivative. And we can plug in b equals 2 for that. Sorry, I forgot to check that this is, in fact, the max. So that's what I'm doing here. So their second derivative is negative. That means it looks something like this. So that would be a maximum. So b equals 2 is a max. So to find what the actual area is, well, I'll take that area equation we made. So 12 times 2 minus 2 cubed. So that's 24 minus 8. And that's going to be 16. So the area will be 16 square units. So this next one gives us the function a is given by a of x equals the integral from 0 to x of t squared minus 2t dt. Determine the coordinates of the inflection points of the graph y equals a of x. Well, our inflection points happen when our second derivative equals 0. So that means I'm going to take my a of x, and I'm going to take two derivatives. Well, my first derivative, well, that's going to go back to that fundamental theorem that we've been talking about a couple times in this. Maybe something called the fundamental theorem might be a little important to remember. So make sure you got those down. So it's going to be x squared minus 2x. So if I know that a prime of x is x squared minus 2x, well, my inflection points are going to be when the second derivative is 0. So a double prime of x, which is 2x minus 2. I'm going to take that, so them equal to 0. So I get 2 equals 2x. So I get when x is 1. And that's going to be my point of inflection. And it wants us to know the x and y coordinate. Well, x coordinate is 1. And then for the y coordinate, well, we need an integral from 0 to 1 of t squared minus 2t dt. Taking our antiderivative, we'll get t cubed over 3 minus t squared from t equals 0, from t equals 1 and t equals 0. Plug in the 1, so we get 1 over 3 minus 1 minus, and plug in the 0, go away, so it's going to be 1/3 minus 1, that's the same thing as minus 2/3. And that is our inflection point. That's it in terms of our videos. If you have more questions or anything, stop by the MLSC, let us know. And if we, we hope you do really well in your exam, and we, wish you the best of luck. So thanks.